There was a brief introduction that I did last time about stars, but today let me continue from there. Just to so let me continue from there, and so what I have discussed is that so for overall about stars. So I just gave you a small introduction about what is a star, and then so I have added something more here just to give you a better understanding. So that is, if you look at, I mean, in terms of the practical sense, if you look at a sky in a dark, clear night, maybe I had these slides even some of the lectures before as well. Uh, the objects that you see up in the sky is like almost all of them are actually stars, right? And there are actually some planets and other stuff, but most of them are stars. And these stars are actually very much similar to what we have on the daytime, right? Our sun is itself a star, right? So it's the main power source for us as well. But at the same time, all the stars that you used to have in the sky, so they are somewhat similar to sun, but there are different properties and different temperatures that they have because they are in like different lifetimes in their process, but they are actually quite similar. Most of them, there are actually when you will see that when we categorize these stars into different spectral classes during this lecture, so there are a lot of stars that belong to the same category as the sun, so which are like quite similar. Um, Now, the one interesting that you have to look understand also have need to think about is that almost all these stars that you are looking at in the sky are actually part of our galaxy, which is the Milky Way, right? So this may be something that you haven't thought about, and something like very basic in astronomy, because when you go outside and look at this the sky, you will see like a huge number of stars. Now on average, if you look at the sky on a very clear night, there will be around like three to maybe 2,000 to 3,000 stars that you can see up in the sky, right? But it is actually not the case if you are living in a city or something like that, because you get then much more light pollution. Especially if you are in this northern area, I know that you don't have much mountains and coverage, that you probably have a better sky. So that's what my assumption. So I'm going through my presentation, and please let me know if if you cannot see the presentation, right? Now, when we talk about the stars, the next thing that we cannot avoid actually talking is about constellations. Now, in general, when you look at the stars, they do not seems to be appear to move noticeably with respect to one star, right? All the stars will move in a certain way, starting from east towards the west, but they normally don't appear to move with respect to one another. Right? So there is actually a small motion which we called as stellar motion. We will learn later, but on average, they seems to be like fixed with respect to one another. Now, these stars, uh, they have a recognizable pattern that persists for many thousands of years, right? So this is what we called as constellations. Now, these constellations, now in modern astronomy, we have well-defined 88 constellations that we know, and this is a standard now. And in the ancient time, when these people, so when they are categorizing these star patterns, they actually did not have this kind of like standard system for constellations, but in the modern astronomy, we use this standard categorizations of constellations, and we now have around 88 standard constellations defined by uh, astronomers, right? And some of the examples that I have given here, Taurus, Pisces, right, those kind of stuff. Now, now one interesting thing that you probably should know is, maybe I have mentioned this earlier as well, these stars that you see in the given constellations are actually not physically close together in the space, right? So they are actually a chance of alignments of these stars that lie at different distances. Sometimes actually, if you think about these things, for example, let's say you look at a particular constellation and it seems to you that all these stars are on one plane, but the actual situation is that if you think about like two of these stars, they may be apart from number of light years, like maybe hundreds of millions of light years apart each other, right? Right. Now let's look at in the practical sense when you, so actually I added these slides, these new slides to you just to give you a practical idea about how the stars looks like, and when you observe how they move around the sky for different locations. Now remember in early lessons we have talked about the celestial equator and the celestial sphere, right? Make sure that you have a good idea about those. And if you, uh, so if I just remind you the celestial poles, which is the northern and southern points on your horizon, basically. Uh, so these are actually celestial poles are uh, what we call as this most northern and southern 2 points of the celestial sphere, basically. And all these stars that you look at basically rise from east side and they set straight down on the west side, right? I mean, if you are on the equator, which is what is more applicable to us because our latitude is very close to the equator, and we are just about the equator, like around 5 degrees above the equator. So we are almost on the equator, and this particular scenario is what is most applicable for us. And during a 24-hour period, all these stars, so they uh, will spend like half of their time above the horizon, and but we will not see those stars for all 12 hours because if the sun is too bright and if they are at the same time, if the stars are rising at the same time, then we may not see those stars for some time, right? So even though it tells 24-hour period, all the stars rise and set for half and half time, like for 12 hours, we may not see those stars in all the at all the times, right? Now, if you move into a different location, like for these upper latitudes, for example, to a country like United States or Europe, so which means you are a bit up in latitudes towards the northern pole. Now, the northern celestial pole is neither overhead nor on the horizon, but in between. You know, the rule here is that I have given here an example. If you are in a latitude of 38 degrees north, your north celestial pole is also 38 degrees above the horizon. So these two are equal, right? I mean, this is just basic geometry. If you think about the celestial sphere, you can easily understand this, right? It will be 38 degrees above the horizon. And now since we are, if I go back to the previous slide, since we are actually very close to the equator, uh, so uh, our actually, let's say we are if we are at the equator, then our latitude is 0. Right? If our latitude is 0, then we will see the North Pole and the South Pole at the 0 latitude, which means in the horizon. So that's why I have mentioned here celestial poles are at north and south points on our horizon. Right. So let's look at the next slide. Is that if I explain further more about this mid latitude, for example, 38-degree north latitude, south celestial pole is actually 38 degrees below the southern horizon, right? So because of that, you will not, it will never visible, right, for you. Now, the advantage for us is you can understand now, since we are on the equator, we will see half of southern sky and half of northern sky, right? So that is the advantage that we have. Now, there is a specific area on the sky that there are certain stars that they will never rise or set, and they will be just rotating around the North Pole, right? And this particular region or the window we used to call as the circumpolar zone or circumpolar window. And the amount that belongs to this particular uh, area is actually defined as, sorry, not defined as, based on your latitude. For example, if you go for the North Pole, all the stars that you would see will never rise or set, because you will see that all the stars will move in a circular pattern. But if you go for this 30 degrees latitude, then your North Pole is 38 degrees above the horizon. So stars within 38 degrees of the North Pole, they will never set or rise. So they will be always above the horizon in day and night, just rotating around the North Pole. Right? And this particular region is we called as circumpolar zone or circumpolar window. Right? So that's a specific name that I expect that you should remember about this particular region. You may not have heard about this before, right? That is called circumpolar window. And for examples for those kind of stars are actually, probably you have heard about this constellation Big Dipper and the constellation Little Dipper, right? And there is another constellation called Cassiopeia, right? So these constellations are, if you are on a country like USA or Canada, these constellations are actually circumpolar constellations, or they are basically located in the circumpolar zone, right? And what that means is they will never rise or set, say they will just go around the North Pole, right? So that you can see those throughout the day. But of course, when it is daytime, you can't see those. But uh, that's how it works, right? But for us, what happens? Since actually we are on the equator, if you are on the equator, your North Pole is on the horizon level, right? So we will not be able to see these kind of circumpolar stars, practically, because we are almost on the horizon, right? I mean, a little bit up on the horizon. So assuming that we are on the horizon, we will not have a circumpolar window like that for us, right? Now, if I just show you using a diagram about these star circles at different latitudes, and this is kind of a summary what I have told up to now. about how the stars looks like depending on your location. Now, for example, if you are on the North Pole, this diagram A is what is more relevant to you. So if you are at the North Pole, the stars circle the zenith and do not rise and set. Basically, it's all the stars will circle around your zenith. Zenith is the point directly above your head, right? If you are an observer and on the North Pole. Right? So that is basically actually, let me, so this part right here, right? So that those circles that you see, they are actually those are circumpolar stars. And if you go to the second diagram, this one right here, when it is close to equator, the celestial poles are now on the horizon. So what will happen is the stars just rise straight up and then set straight down, right? You will not see a circumpolar window like that. Now, if you are in the mid latitude, like this, somewhere here, this is like a this is like a mid latitude right here, and then you will have a region on the sky directly above, not yes, just towards this is the celestial North Pole, and what will happen is then you will have a region of the sky again in an intermediate latitude that all the stars in this particular region right here, you can see from these white circles in this particular region, they will never rise or set. So I have mentioned here at intermediate latitudes, the north celestial pole is at some position between overhead and the horizon, right? And its angle above the horizon turns out to be equal to the observer's latitude. Stars rise and set at an angle to the horizon. Right? So I guess once you read through, this will be more clear for you. Right. Right. That's basically a brief introduction for you about how the stars looks like, how the movements of the stars happen depending on your location on the earth, right? So you can say that for different regions of the world, you will see different stars and different constellations, and they will rise and set in a quite different way. And this is actually just to catch your attention that this is the constellation Ursa Major or the Big Dipper, which is shining over and the picture is taken from one of the roads in Canary Islands, and this is in Spain, which is a very popular place for observational astronomy. And I guess we had some telescopes there as well in Canary Islands. One of the beautiful places for observation for the stars. You can directly see from this picture itself, and in the image you can see that there are large number of stars, and out of those there are is a constellation. It goes like that. Did anybody understand this shape? And there is some outer part as well. Now this is actually which constellation? This is the Big Dipper, right? So one of the popular constellations is the northern sky. But for us, this is a little bit down for our location because we are close to the horizon now. So this is a constellation close to the North Pole. So which means when we are looking from here, this particular constellation will be uh, down or close to the horizon on the sky, right? Right. So those are just an introductory section for about stars. Now we will go into more like stellar properties and those kind of things which we have started last time. Right. So this particular picture, let me start from this particular picture that you see. The picture is actually a long time exposure of a camera. So that shows different colors. of stars. And you can see each circle has different colors. So it's like a colorful picture of circles. But what has actually happened is this particular image is taken from a with a long exposure time from a camera. And these circles are due to what? Circles are actually due to the rotation of Earth. Right? When the Earth rotates, you get these circles. Right? You know that it's actually not the stars rising from east and setting from Earth. What actually has happening is when Earth is rotating with respect to us, star seems to rise from east and set from west. Now this is the result of a long exposure. So what I want to convey here is that you can see that different colors for different stars, right? It's like a colorful circles. So which means now you can see that stars are actually from different colors, right? And these colors are actually comes here. So these colors come here because they have different temperatures. Stars have different temperatures, so that they will these temperatures represent from the colors, right? So that's what has happened. You know that when it is a high temperature, you have different colors now, right? When it is go higher, it will become like white, like that, right? So that's what represent here, and we will see how that is related to our physics, right? What laws that we can use to relate this color to the temperature, right? So this is basically something we can explain from the Wien's displacement law. And the questions actually we are going to answer in this particular lecture, and maybe in the next day as well. Also throughout this maybe next 5 or 10 lectures is that how these stars are born and what are they made of, and then how far away these stars and how long they will live and how they will die. So these are the questions that we have to answer. Now in observational astronomy, there is only one way that we know of answering these questions. It is by actually decoding the messages contained in the light and the radiation that reaches the Earth. Now, you know, all these stars, they will emit some light and radiation which will come into Earth or at least to the space. So we will use telescopes to collect these lights and then decode the message that are giving, they are sending us, right? In that way, we will be able to understand these properties of stars, right? So how they are born, what are they made of, those kind of things. Now to understand, we are basically looking at a few properties. Uh, that's what I have already mentioned you last lecture. That is the brightness, color, distance, size, temperature, age, life expectancy. So these are the basic properties that we are going to measure from a star based on what we are getting from our telescopes, right? Basically from these light photons, right? Now in this particular lecture, I'm going to show you how we can do that and what are the equations that we will use for these measurements, and basically how they are derived, like for basic understanding, those kind of stuff, right? Now we will discuss how astronomers go about measuring these many of these properties, and also see how that many of these properties are related to one another. And you will see that some of these properties are actually related to one another. For example, magnitude and brightness, uh, they are related, and also uh, the temperature and the color of a star is also related, right? So that's how those things work. And uh, the goal here is to use these properties to develop an understanding of the many different stars that we see. You can see that we are seeing millions of stars, right? So we will use these properties to understand these different stars that you see in the sky, right? Now, the first thing I am going to talk about is introduce the luminosity for you. Now, luminosity of a star, as in any other lesson, the total amount of energy at all wavelengths that it emits per second. So that is how we define the luminosity. Now, to make a comparison among the stars, so we are basically looking at different stars and try to compare the luminosities of these stars. We are astronomers actually express the luminosity from a different unit. So that is in terms of the sun's luminosity. So that means uh, if I take an example as the Sirius star, so we used to tell that Sirius is about 25 times uh, luminous compared to the sun, right? Now, the unit that we are going to use is the unit that I have written here, this unit right here. So this is basically L naught or this dot at the middle. So this means the sun's luminosity, right? Luminosity of the sun. So if in any place that you see the luminosity of Sirius is like in this symbol 25 L like that. So what this means is Sirius star is luminous 25 times more than the sun, right? If you compare it with the sun's luminosity. So that's how we basically write the luminosity, right? So this is something that you wouldn't think, right? The sun Sirius is luminous than the sun. Now this is why. Anybody have an answer why the luminosity, even though we see the sun as like a big star, right? It gives all the luminosity and the brightness of us. Now when you make measurement, why is that Sirius is more luminous than the sun, even though if it doesn't look like to other. Anybody have an answer for that? Why is that?
Actually, sir, the Sirius is so far away from us than the sun. So even
Yes,
though the sun is less luminous than the Sirius, we are seeing as it's bright.
yes, exactly. Thank you. So that is the reason. I guess all of you can understand it, right? It is basically simple, but still nice to see know about that, right? That is about the luminosity. Now let's look at the apparent brightness of a star, right? So the apparent brightness is amount of uh, apparent brightness is the amount of star's energy that reaches a given area each second here on Earth, right? So this is basically how much uh, oh, wow, the amount of energy that reach for us from a star, right? This is the apparent brightness. Now, this if you in terms of the apparent brightness, actually the sun should be larger, as she told, because the sun is closer at. So it's if you look at the apparent brightness, sun seems to be more brighter compared to other. Now, so there are actually wide range of apparent brightnesses among these stars that you see up in the sky, and most these stars, in fact, are so dim that you need a telescope to detect them, right? And if you remember that I told you these limits that we have in terms of the magnitude that you can look from the naked eye, right? From the magnitude scale that we have talked last week, I will talk that again here as well. It is the sixth magnitude limit is the naked eye limit, which means anything fainter than the sixth magnitude, you will not be able to see from your naked eye, right? And now, if we have two stars with the same luminosity and one is twice as far away as the other, it will look 4 times dimmer than the closer one, right? I hope you can understand this. This is not only valid for stars, but also valid for everything else, right? Basically, if you have two objects with the same luminosity, if one is far away, so this will be, it will, if, for example, if one is 2 times far away than the other, the one that is far away will be 4 times dimmer than the one that is close by. The reason is this actually. So you know that when you, this is in the inverse square law of light. That is, when light radiates away from its source, it spreads out, right? And this is the simple thing that I guess you already know about that, but just to complete the note, I put it here. And so when you go far away, you can see the light spreads out so that the amount of energy that you receive will be less, right, from the object that is far away because of the spread of the light. And this is what we called as the inverse square law of light, right? Now, this brightness that you see in an object, so astronomers actually have uh, derived an equation, and also they have this what do you call this scale to measure these brightnesses. And this measuring brightness of a star is actually called photometry in astronomy. Sometimes you may see that if you hear from I mean, if you hear a talk from some of these professional astronomers, they used to use this word photometry and astrometry regularly. Photometry means actually measure nothing special, that is about measuring the brightness of a star, and they are using different techniques for that, right? Like measuring brightness of a star is a main thing in astronomy, so that they have this specific word called photometry. So this astronomical photometry actually began with Hipparchus in 150 BCE, right? So what he did was, I think I discussed about this last time as well. He prepared the catalog of nearly thousands of stars that include not only their positions but also estimate their apparent brightnesses. So he has a catalog of 1,000 stars, and also he has estimated the apparent brightnesses of these 1,000 stars, right? Now what he has done is, now he has a large sample with different brightness values. So he sorted these stars into 6 categories, right? And each of which he called as a magnitude. Now this is how this magnitude scale came into astronomy. And so what he actually did was, he looked at the brightest stars in his catalog and he gave a number for that. That is the first magnitude stars, right? Number one. And for the fainter magnitudes, that stars that he could barely see, he gave them as the sixth magnitude star. Now you can see that how this naked eye magnitude limit came into play, right? At his time, he was only looking at star maybe from just from the naked eye. The stars that he can barely see, he gave the number six, and the stars that are very bright, he gave the number one, right? Now you can see these numbers. Once the numbers go up, the stars get faint, right? So this is why magnitude scale is working in the reverse way. It's like a historical thing. That's how it came out, right? Because they did not have these telescopes now at that time, so they were just defined the magnitude scale in this way. Now during the 19th century, the astronomers actually attempted to make this scale more precise by establishing exactly how much apparent brightness of the sixth magnitude star differ from that of a first magnitude star. Now, in the Hipparchus time, actually, he just look at the stars and categorize them into different categories, then assign numbers. Then after that, in 19th century, what astronomers did was actually they look at actually uh, when you consider a star with the one magnitude and the sixth magnitude, they look at what is the brightness difference, how much brighter if you compare two stars, right? And so what they were actually found, and what we are actually using now, is that difference of these 5 magnitudes correspond exactly to brightness ratio of 100 to 1. So what this means is, if you get a star with a magnitude of 1 and a magnitude of 6, the magnitude 1 star actually 100 times brighter compared to the sixth magnitude star. Now you can understand that this is not a linear scale, right? Magnitude and the brightness. This is like a log scale, right? right? Now, based on what they have, they devise this equation, that is, if you have two objects with magnitudes of m1 and m2 for two stars, then you can calculate the ratio of the brightness, which is b2 over b1, using this equation, right, right here, right. So this is the equation that relates the brightness and the magnitude, and this is based on that finding that they had about, like, when you have one magnitude bright star is basically 100 times brighter compared to the sixth order magnitude, and then you can do a few calculations and obtain this particular equation if you need. I mean, you don't have to, you can still use one of these equations as well. They all basically will give you the same value at the end, right? Just just to make easier to do some calculations, we have like different deviations, but I would like that you remember one of these equations, right? It doesn't matter which one, but make sure that you remember one of these equations for your exam, right? These are like basic equations in astronomy that I expect that somebody who is doing astronomy should know, right? Now, based on this equation you have, I can probably give you a question that is, it is a common misconception that Polaris, which is a North Star, which is a magnitude of, it has a magnitude of 2.0, is the brightest star in the sky, but the distinction actually goes to Sirius, which has a magnitude of minus 1.5. And the question is, how does Sirius apparent brightness compare to that of Polaris? Basically, you need to find uh, Sirius is how much. Sirius is basically how many times brighter compared to the Polaris, right? Can you try this based on the information that you have? So I will give you like 5 minutes. So try it yourself, and then let's. Uh, Once you have the answer, please post it to the chat message so that we can discuss about it, right? I mean, if you don't have a calculator, just keep it like a rational number with like a half or without decimal, like a ratio or something like that. That is fine as well. But if you have a calculator, you can basically take the answer that the Sirius is basically how many times brighter compared to the Polaris star, right? You just need to use this equation, right? So I want you to practice this a little bit. So let me give you a few minutes to do this so that I will uh, be here until you complete it. So let's just try to uh, do the calculation yourself and post it to the chat window. So I will wait for some time for you to do that. Right? And while you are doing it, if anybody else also have a question, you can ask as well. Right. Right. So the answers are correct. And basically what you need to do is just substitute the magnitude values to this equation. That only thing that you need to be careful is you can see that when you write B2 over B1 on the right hand side, it is M1 that comes first, right? Most of the students, this is the place that sometimes these things can go wrong, right? So make sure that you actually remember one of these equations, either this one or one of the others, because once you know one of these equations, you can derive the other two easily, right? You don't have to write, like, remember everything, right? So let me go back to our presentation, right? Now this scale I have shown to you, I guess yesterday as well. These are like different limits that you can see depending on these magnitude values. Now the magnitude for the Sirius, as you see in the previous problem, is around -2, which is like around this region right here, which means that particular star Sirius should be able to, you should be able to see it from your naked eye, right? Because it's above the naked eye limit, goes to a lot with minus values. And Polaris, by the way, it's a yes, it's a magnitude 2 star, and you can see that it's around like somewhere here, a little bit fainter compared to the Polaris, but you can see in terms of the brightness, it's 25 times less brighter than the Sirius, right? This misconception comes actually from the fact that we normally talk more about North Star, so everyone thinks North Star is brighter, but the, the real thing is Sirius is more brighter for us in terms of the apparent brightness. Right, and this is also a nice diagram that kind of scale up different places that you see in this magnitude scale, and you can see that the sun is right here, even just outside here. It's standing in an extraordinary position in this scale, right? It's -26 point something like that, as far as I remember. And the full moon is the next brightest one on the sky, right here. And then the Venus is actually really bright. If you see up in the sky, that's close to -4. And Jupiter and Mars, so when they are at brightest, they are also around -2, maybe -3. Yes, around -3. And Sirius counts next. And you can see that these planets are brighter, right? And then the Alpha Centauri is the nearest star for us. It's kind of at the 0 point, and that is also visible. And then Betelgeuse, surprisingly, Betelgeuse is right here. By the way, all these stars you can see up in the sky if you go outside, right? Sirius, I'm not sure. I need to look at the star map, but Betelgeuse is one of the stars in the Orion constellation that you can see. Now, the Polaris, because Polaris is the North Star. The North Star is very close to our horizon, so not sure whether you can see it if you are not in a place where the sky is dark, plus that you should have a good view of towards your horizon to have that view. And then the other, these stars right here, there is something called Bernard star. Bernard star is one of the stars that has a very high proper motion, so which we will talk about in one of these next lessons about stellar motions, right? And magnitude 10, so that is the faintest object visible to binoculars. Now if you have a pair of binoculars, you can go up to magnitude of 10, right? And then this is the 1 meter telescope limit. And I guess now you know what, when I tell 1 meter, what does that mean? You know that. And this is the 4 meter telescope limit. See how it's interesting that you can go up to this limit, right? And here is the Hubble and Keck telescope limits. Hubble is actually a space telescope, and I guess this should be Keck telescope, which is not clear here. Keck telescope is a ground-based telescope in the mountains of one of these mountains in Hawaii, which is also a place. I mean, I would say that one of the nicest place to observe observations in the world because of clear skies and these high altitude mountains. So you can see that, look at the fainter objects, you need to go to these kind of large telescopes and maybe to the space to get those things cleared, right? Right. So that is about the magnitudes. Now, magnitude, we just use a number to measure it, right? But if you go for other wavelengths, remember that we talked about radio astronomy, X-ray astronomy, those kind of things, that if you go for this magnitude scale actually mostly used for visual astronomy, which means to these optical telescopes to look at optical wavelengths. And but this is actually not used in these new branches in the field of astronomy. So what that means is, if you If you become a radio astronomer, so that means work with radio wavelengths and radio telescopes. So they measure the amount of energy as energy being collected each second by each square meter of a radio telescope. So that's a different unit, right? And this is expressed in brightness of each source and in terms of, like, for example, watts per square meter, like that. Now, for the uh, infrared, X-ray, and the gamma ray astronomy, we use normally energy per area per second rather than magnitudes. And you can see that astronomy is a very like vast field that when you go for different these new branches, for example, X-ray, gamma ray astronomy, and X-ray astronomy, they use different types of units, right, for those calculations. So you don't need to know like too much into detail about these things, but have this information in your mind in one day in case if you have to use those. Right. Now we talked about the brightness, how we can get an idea about the brightness of a star. Now let's see how we measure the distances to stars, right? And this is, I mean, brightness and distance is basically like two main things that we are going to measure for a star. Now, you know that even the nearest star is very, I mean, too far away from us. I mean, we cannot even think about traveling to those stars right now. You know that Alpha Centauri is the nearest star, which is around, as far as I remember, 4.2 light years or something like that from away, light years away from us, right? Now, if you convert this into numbers of years, you can't even think of traveling to that particular uh, star. You can think that 4.22 light years means if you go in a uh, speed of light, it will still take 4.2 years. Right? So this will be a huge, uh, I mean, huge amount of time. Now, because of that, astronomers actually use some indirect methods to measure these stellar distances. Now, one of those methods are called parallax. In fact, one of the very successful methods in astronomy now in modern days to measure distances. And this is also a very simple method that anybody can easily understand. The parallax actually is defined as the apparent displacement of a nearby object relative to more distant objects as the observer's location changes. I think you all know about this. Let me show you a diagram that you can easily understand. And you can see that, so you are the observer here. And once the observer location from changes from here to here, you can measure the change in the angle with respect to background that you see, right? For this particular image, that is this mountain, right? So we will use the same method to measure these angles in astronomy. And then once you measure this angle, you can actually convert it into a distance. And this is how you do it. An object with parallax angle of 1 arc second, and I assume that you all of you know about arc seconds, right? Uh, Lies a distance of 3.26 light years away. So this is the definition, right? And this distance actually we called as 1 parsec. So this is the new unit that we are going to use when we talk about stellar distances. Because the distances are so far away, even the light year is not enough for us when we talk more about stars, right? Now, an object with a parallax angle, normally we uh, denote from letter P with zero point 0.1 arc seconds, will have a distance in terms of parsecs if you substitute the value 0 0.1 here. So can anybody just find the answer and tell me now? It's just a simple calculation that you can either unmute your mic and let me know the answer, or you can directly post it to the chat window, whatever you like. Now, this is a very simple one, right? I would like anybody else other than who answered these questions, if they can answer, that will be good actually. Just you need to plug the value. I mean, you don't even need a calculator to give the sounds. Right, thank you. This is 10, right? 10 means 10 parsecs actually. And this equation is very important in terms of the units, right? Make sure that when you substitute a value for this equation, the angle that you are going to substitute here should be in terms of arc seconds. None of the other units will not work, right? The angle should be in this units in terms of arc seconds. So that's why I have put it inside brackets. And once you plug this value in terms of arc seconds, the answer that you mentioned rightly as 10, the unit of that answer should be in terms of parsecs, right? For example, if I take another example, let's say you somehow measured the parallax angle of a star, let's say 0 0.5 arc seconds. So if it is 0.5 arc seconds, you divide 0.1 over 0.5. So that means basically how much? So that is 1 over 0.5 means it's 2 parsecs, right? So that's how you normally find the distances. Remember, once again, the units are very important here. The parallax angle should be substituted in terms of arc seconds. Now let me put it in this way. If I, let's say, if I give you a problem telling that, okay, this particular object has a parallax of from a different unit, let me use arc minutes, right? If I tell you, okay, the parallax of this particular object is 0.02 arc minutes, then you cannot directly plug 0.02 here. What you have to do is convert that into arc second. That means you just divide it by 60, right? You know how to convert the units. And then you have to substitute that converted value to here as the parallax angle. Then you will get the answer in terms of parsecs, right? So that is the proper way of using this equation, right? You can see that it's not only the equation that you have to remember, and also I expect that you should remember this equation, right? These are like basic equations in stellar astronomy, right? And if anybody like had, I guess you know about this, I am not going to explain it. If anybody like have an doubts in how to convert the arc seconds into minutes, so I have mentioned it here. Basically, degrees, uh, 360 degrees in the full circle, and then it is subdivided into 60 equal. 1 degree is subdivided into 60 equal parts, and one of those is arc minutes. And when you divide arc minutes again into 60, you will get arc seconds. Right? So you're just dividing all these things by 60. I guess I'm not going to explain this, so I just put it here just to make sure if anybody needs a unit conversion. Now this is the same concept, how it looks like when you do actual measurements. Uh, Now this is the sun is at the center, and we know that from sun to earth we have a distance of 1 astronomical unit, and the parallax angle is this one right here. So once you measure the parallax angle, uh, then you know that earth is rotating around the sun, and you can measure the angle again from here. Then you know that the distance from here to here that you can calculate in that way. I mean, it's just to give you get you an idea about how this distance is calculated, right? Distance is d right here, right? So now let's look at a little bit more into this parallax angle. You can see that the parallax is actually depends on the distance is basically depends on parallax angle. Now, if the object is closer to you, then you have a greater parallax angle. And you know from that equation, the parallax angle is actually inversely proportional to the distance, which means if the parallax angle is higher, then the distance to that particular star should be smaller, right? So that's how it works. So make sure that you get that into your mind so that you can get an idea if you need to compare the distances to two stars. For example, let's say if I give you two parallax angles of two stars, and I will be asking which one is more closer by how by like how many factor, you should be able to answer, right? Basically, the first thing that you should get as an idea even before the calculation is that the larger parallax angle object will become more closer to us, like that. So that's what I have mentioned here. The largest baseline, the larger the parallax will be. And right, so let me go to next one. Now let's look at uh, how this parallax is used in astronomy. This is just how it is actually calculated. Now, in order to have a larger baseline possible, we can observe stars from opposite sides of the Earth's orbit. So that's what you have seen in that picture, right? So after 6 months, our Earth is on the other side of the orbit. So we know that we are moving in an elliptical orbit. So from one, when you go from one side to the other, takes like 6 months, right? And the length of the baseline is 2 astronomical unit because for one side from Earth to Sun we have 1 astronomical unit, and when it go to the other side it will be 2 astronomical unit. Now the parallax angle P is the half of the angle that the star will shift as a result of this movement. Right? I guess you can understand it now. This is just how you calculate it, right? Now using this parallax technique, actually, you may have this question now. We are talking that we will use parallax angle to measure the distances to these stars. Now, the one question maybe you have in your mind is, do astronomers actually use this, or this is just a textbook thing? This is actually not a textbook thing. So there are instruments, satellites that we have sent specifically to measure these parallax angles, and this has been very successful. And astronomers have measured precise distances to thousands of stars. Now, actually, this is actually not thousand. Astronomers have measured the distances to billions of stars. Right? I have all the data now download by myself. Actually, very recent uh, mission, which we called as Gaia satellite, is specifically sent out to the space to measure these parallax angles for stars in our Milky Way. And it has taken measurements of, I guess, close to few billions of or few millions of stars, right? And there is a large catalog now that we know a lot of details about these stars, including the distances to each of these stars. And these are like very precise measurements, right? Taken. So this data actually came like one, not maybe not 2 years ago, even maybe 1.5 years ago is the time that they have released this the latest data release for this parallax angle. And this slide is actually a bit older in that sense. Uh, the Proxima Centauri has the largest parallax angle of all known stars as expected, right? Uh, you know that it is the closest neighbor for us. I mean, not only for us, also for our sun. So that has a parallax angle of 0.77 arcsec. So which means you can now convert it, right? And find the distance, and you will see the answer will come in terms of parsecs, by the way, right? When you convert this into the distance using that particular uh, equation. So I guess you can do it yourself now. Now, once you convert and find the distance, that will be the distance well, that comes in terms of parsecs. So you have to convert it into light years if you want the answer in terms of light years, right? Sometimes even in exams, you used to get these question like, maybe I can give you the uh, uh, parallax angle measure, one of the measured parallax angles from one of these satellites, and I will ask, okay, find the distance to this particular star in terms of light years. Then what you have to do is, first you have to calculate, use the equation and calculate the distance, because I am giving it in terms of arc second. So you will calculate it, uh, and then you will be finding the distance in terms of parsecs. Then what you have to do is actually convert it into light years. Now you know that I have actually shown you uh, 1 parsec is equal to 3.26 light years. So you just need to multiply it by 3.26, get it in terms of the light years. Now these conversions actually you will be given in an, if I give it an exam, I will give that conversion like 1 parsec equal to 3.26 light years. But if you are into more into astronomy field, it is always useful to remember those, I mean, small conversions. This is like everybody knows know how many grams that you have for a 1 kilogram, right? I mean, everyone can tell that because you use it regularly. For astronomers, parsecs and light years are like that. Every astronomer used to know that, okay, 3.26 equal to 1 parsecs, like that. Now, one of the older examples of making measurements of the parallax is actually this Hipparchus satellite. So it actually you measured the parallax angles of around 100,000 stars. And this telescope, it has actually precision of 0.002 arc second. Now, this is one something very practical that you can think of, right? Now, this particular telescope that they have with the satellite has a precision of 0.002 arc second, right? And if you convert this into parsecs using the same equation, then your answer will be 500 parsecs. So what that means is, since this is the precision of the telescope that you are using, you cannot measure the parallax angles of the stars beyond that, right? So what happens if you measure it? Then what will happen is actually your measurements will, accuracy of the measurements will get, uh, I mean, accuracy is not that good, right? Because you are going to the limit beyond what the instrument can do, right? So this is why actually these are the practical limitations for these things. You know, when object is very far away, when you go far and far away, then the parallax angle becomes smaller and smaller. Now your instrument should be able to measure it, right? Now Hipparchus satellite has the precision up to 0.002 arc second. So when it becomes even smaller than that, the satellite cannot measure it. So that is the limit of this particular satellite. Now, when we send this Gaia satellite, it has a good precision than this one. So that's why it could measure actually a large number, parallax of large number of stars, even uh, more far away than this. So I can't remember its precision, but I will probably give you a few information about that the next day, right? Now, this is one reason actually why we cannot use the same method to measure the distances to more remote stars and galaxies and stars that are very far away from us. Now, these stars that they have measured, remember that all these stars are in our galaxy, by the way, Milky Way, right? If you need to measure the distances in astronomy to these faraway galaxies, which are like millions of light years away from us, this method will not work, right? For the reason that I have just mentioned, because the parallax angle gets smaller and smaller, so that it will become hard to measure from an instrument, right? Now, you probably know that best example is in your laboratories, you may be using multimeter, right? So if you need to measure, let's say, 0.001 nanoamperes, it is hard to do that, right? Because if your multimeter does not sensitive to in that level, you cannot do that. So same thing applies here, right? And because of that, we will use different techniques to measure the distances to those remote galaxies, right? And that will be actually interesting that we will talk about that. So if I mention it briefly, we will use type 1a supernova, which is one of the nice, I would say very nice phenomena is that would happen to a star at its age of end of the life, in end of its close to the end of its lifetime, and we will use this supernova cores to measure the distances to these that are very far away from us, and also we will use the redshift of galaxies to make these measurements. And I personally have used that, and I can tell you how to do that when it comes to that particular section if time permits. But for now, for the stars that we are talking within our galaxy, we can mostly use this particular method. Right. So let me go into the next phase. Now we know how to measure the distances and we know how to measure the apparent brightnesses, right? Now this doesn't help to compare the brightness of two objects, by the way, because if you look at, for example, now you also said that sun is brightest for us because it is closer to us, right? Now we need to, if you need to compare the intrinsic brightness of two objects, this magnitude scale that we have learned using the apparent magnitude or the apparent brightness will not work, right? Because you cannot get an idea about the intrinsic brightness about these stars. Because one that is closer to us seems to be brighter according to that particular scale. And because of that, the goal of our study, for goal, excuse me, uh, now the goal for us is remove this effect of the distance and treating all stars as they were at the same distance, right? So that is what we can do. That is, we if you need to compare, for example, Proxima Centauri and our own sun, we have to keep both these objects at the same distance and then look at the brightness. Then this is how you can get an idea about the intrinsic brightness, right? Now this is done using something called absolute magnitude, right? And absolute magnitude is actually has a specific definition. That definition is that if you measure any object's apparent magnitude by keeping that particular object at a distance of 10 parsecs, that is called as the absolute magnitude. Now it is very important that you remember this definition, right? Once again, what you need to do is you have to keep the particular interested star or the stellar object at a distance of 10 parsecs. You are not going to keep it actually in that place. You cannot do no. But when you do the calculation, you assume that it will be at a distance of 10 parsecs and then you measure the magnitude. And this is called the absolute magnitude. Now the advantage is since you are defining a particular distance, which is 10 parsecs, you are going to keep all these stars at that particular distance from 10 parsecs, so that you will have the advantage of looking at the intrinsic brightness. So compare the brightnesses of these objects, right? So that will be our next task, right? Now, this is called the distance magnitude relation. That is, to determine the absolute magnitude of a star, we need to know its apparent magnitude that we can find, and we need to know the distance. Now, you know, we can find the distance to these stars using the parallax method, right? Now, if you know the distance and the apparent magnitude of a star, you can find the absolute magnitude, right? Now, to relate these quantities, we need only account for the inverse square law dependence of the brightness on the distance, right? That is, you need to know that also. You remember that the brightness is proportional to 1 over d squared, right? So using that relation, apparent magnitude, that we know it's a logarithmic factor, because a factor of 100 in brightness correspond to difference in 5 magnitude. So we use that particular fact to derive an equation that relates the absolute magnitude, apparent magnitude, and the distance, right? That relation is what you are seeing here. The relation between the absolute magnitude, apparent magnitude, and the distance. Now, this is like an equation again that you should remember, right? Every astronomer used to remember that this equation, this is like F equal ma type equation in astronomy. So make sure that you remember this equation. Even if you don't remember, you can easily derive it, right? From here to here with the given information, like you define absolute magnitude as a distance equal when it is when the distance is equal to 10 parsecs, and you can see that is what you see here. Once you incorporate all these things, you can easily derive this equation, right? Which will give you this final equation, right? So from this equation, you can see that if you know the uh, right, if you know the absolute apparent magnitude and the distance, you can find the absolute magnitude, right? So let me, so here is an example for you. So let me stop from here for here today, since we are, I guess, almost close to 7:30. So I'm going to stop here.